Welcome to my presentation. My name is Sebastian Ahlmeier, and this is joint work with Nicola Gast from INRIA Grenoble-Rhône-Alpes and University Grenoble-Alpes. Today I will be talking about mean field and refined mean field approximation for heterogeneous systems. First, I want to introduce the classical mean field by talking about an example. So on the left of the slide, you see an illustration of the well-known two-choice model. So this is a load balancing model and works the following way. So we have a constant stream of jobs that arrive, scaled by the system size, which is n in our example, which is denoted by n in our example. And these jobs arrive at a dispatcher, which for each arriving job samples two servers and forwards our job to the server with the least amount of jobs in its queue. In this classical setting, all our servers have the same working speed, denoted by mu, and then after while work. Yeah. So how do we obtain the mean field approximation for this two-choice model? First, we represent our system in using an occupancy measure. So we would describe our system using the percentage of servers with a certain queue size. And then when we scale the number of servers, then in the limit, we obtain a differential equation. And this differential equation now is called mean field approximation. Now, it is known that this methodology works well if all our objects in our system, stochastic system, exhibit homogeneous behavior, so meaning they are statistically identical, or if we can cluster them into groups of statistically identical objects. So what makes the mean field work for this? In this case is that the dependence of objects to one another vanishes as the system size gets large and therefore gets more predictable. What's also possible is if we consider dependencies among objects, we can refine the mean field approximation by approximating moments of the system. What is the motivation for our work? So, in essence, we were interested in heterogeneity of stochastic systems, since heterogeneity can dramatically impact how a stochastic system evolves. Examples for these heterogeneous systems would be caching systems, epidemic spreading, or heterogeneous load balancing models. And what we found is that there were no general results related to the mean field approximation, which justify the use of the latter. So why are we interested in results for mean field approximation? Because mean field allows us to simplify the analysis for these stochastic systems. And also, since it is a differential equation, can be computed very fast by using the numerical tools available. Then, like the leading question of our paper is whether we can justify the use of the mean field approximation in these heterogeneous settings. To illustrate this problem a bit more, I would like to introduce another example, a heterogeneous two-choice model. This is based upon the previously seen example. However, now we're considering n servers, which all have different processing speeds. Now, for the heterogeneous case, we would model our system not by occupancy measures, but we have to consider every server and all of its states individually. And we do that by looking at indicator functions, which represent which tell us whether a server has a certain amount of jobs and at a certain time point. Now, based upon the representation, we can then formulate the dynamics of the system. So in this system, there are two different dynamics. First, the first transition that appears is when a new job arrives and gets dispatched to one of two randomly selected servers. We call this pairwise transition since there are two servers involved. The other one being a unilateral transition when the server just works through a job and the job departs afterwards. Here, for the unilateral transition, there's just the server itself involved until the change just the server itself involved. So this is why it's unilateral. In order to put this in more mathematical terms, so that the unilateral transition decreases the buffer size by 1, and this happens at a rate mu k, which is the server speed, times the indicator function if the server has as jobs in its buffer. And for the arrival, it's a similar reasoning. We increase our buffer size if our server has been chosen randomly and has fewer jobs in the server than the second server that has been chosen. So important to notice is that all these transition rates have kind of a polynomial structure. So we always have a product of indicator functions. And while the indicator functions only take values between 0 and 1 for the mean field approximation, this can be generalized also for values between 0 or 1. Now I want to talk a bit about the generic dynamics which are allowed in order to model these heterogeneous systems. So we allow D-wise interactions, meaning that D is a number that is fixed and independent of our system size, and we allow interactions of up to D objects in this in the same sense as for the two-choice model. So any amount of objects up to D can interact and lead to transitions in the stochastic model. However, the important thing is that the rate at which this happens scales by 1 over n to the power d. And let me illustrate this a bit more. So if we have pairwise interaction, then the rates need to scale by 1 over n. If we would have 3 objects that interact, the rate of that happening would need to scale 1 over n squared up to 1 over n to the power d minus 1 for d objects. So in order to define the mean field approximation, we need to have a look at the drift of our system. And the drift is defined for a certain state as the sum over all possible jumps times their specific jump rate. To illustrate, when we look at a specific server on our heterogeneous JSQ2 model and look at one specific queue length, then the drift of this KS tuple, server queue size tuple, consists of all the possible actions that lead to having the S servers, S jobs in our server buffer. So then now having the drift of our system, we can define the mean field approximation as the differential equation following the drift dynamics. Now coming to the results. First, it's important to notice that the drift we find before is Lipschitz continuous and smooth due to the polynomial structure of its entries. And the second, what we assume in order to obtain our accuracy results is that we need our rates to be uniformly bounded and independent of the system size. So now, given these properties, we were able to to show that the probability of an item in a certain state at a certain time is given by the mean field approximation with an error of 1 over n, and also considering the refined refined mean field approximation, the same probability is given by the mean field plus the refinement term with an accuracy of 1 over n squared. I also want to point out that these results allow to obtain approximations for any linear transformation, and such as average values or Q load balancing setting the average Q length. Next, a few words about the refinement and the proof. So our heterogeneous framework allows to refine, to pick up and adapt this refinement term, which follows the ideas of Gaston van Hout and Gaspar Toulouse and Trivaston. And the refinement idea is really based upon trying to capture the dependencies among objects. Nice thing about this refinement term, it's also described by differential equation, the exact linear differential equation, so it can be computed quite efficiently as well. Now, coming to the proof idea. So the proof idea is on a high level. The steps are that we first realized that the probability of an item to be in a certain state is equal to the expectation of the indicator function, xks of t. And based upon that, we want to compare the generators of our differential equation and of our stochastic system and relate those, which is kind of methodologies related to Stein's method. To do that, to relate these two, we apply Taylor approximation and then bound remainder terms using the rate structure we introduced and for the allowed transitions. Next, we come to the numerical results. So the first plot I want to show you is for heterogeneous load balancing model. Here we plotted the average Q length and compare the mean field approximation with the sample mean, and also plotted the refined mean field approximation in orange. So two takeaways from this plot is first that indeed the mean field approximation, the mean field approximation accuracy grows as n gets large. So here we have small system size like 10, 20, 30, 40 items. And you can see that for this average Q length, mean field approximation really gains on accuracy. And then also very important is that the refined mean field approximation is even for these small system sizes very accurate. So it lies within the confidence interval of our sample mean. It is therefore something that's worth considering when working with like small system sizes. Another example I want to talk to you about is the random cache model. Just small high-level introduction of the cache model is that we considered multiple caches, and items with different popularities can move through these caches when they are requested and are then exchanged by a random item in another cache. So what is important about this cache model is that we had steady state, exact steady state values available. So we were able to compute the error between mean field, refined mean field, and simulation compared to these exact values. And indeed, what was suggested by our theorem is that the error for the mean field decreases as 1 over n, and for the refined mean field as 1 over n squared. And also we see that the mean field and refined mean field are reasonably fast to compute. And furthermore, the refined mean field is also very accurate, even more accurate than simulation, especially for n equals to 50. Another table I want to talk about is for the cache model. It's based upon the computation times for transient regime. So here we see that the mean field approximation can be computed very fast. Even for 1,000 items, it takes less than a second to compute. And then for the refined mean field, we see that it also has for a system size of up to 100, it's a fast computation time. And I also want to mention that the refined mean field is very useful in for system sizes of 10 to 100, because it vastly increases the accuracy of the mean field approximation. And then for larger system sizes, it's usually the gain of the refined mean field is not that big, so it makes sense to eventually just fall back on the normal mean field approximation. Coming to the takeaways, so our heterogeneous framework and the mean field approximation allows to model and approximate fully or even partially heterogeneous stochastic systems. We were also able to refine this mean field approximation using this refinement term V. Then I also want to mention that these approximations can be efficiently implemented for example, by using the RMF tool we developed in order to work with mean field and refined mean field approximation. This tool works for heterogeneous settings, but also for the homogeneous case. And then it's also good, and also I want to show you that the hidden constant in our theorems are in practice quite small. So thank you for your attention. And thank you for listening to my talk about mean field and refined mean field approximation for heterogeneous systems.